Hello, and welcome to this session on getting started with Azure Machine Learning. The description of this session is the following. Azure Machine Learning is a managed service that integrates services together for a full end-to-end machine learning solution. Azure ML enables data scientists, data engineers, and business users faster development, deployment, and access to machine learning models. Services that are available for each role include zero-code or low-code designers, Python, R, Databricks, Azure Kubernetes Service, and many more. Workspaces keep assets and artifacts in one place for easy management. Models, which can be developed locally, trained in Azure, and deployed to any device or environment. In this session, we will cover the built-in tools of the service and see an end-to-end solution for a simple machine learning model. Here is a little bit about the company that I work for. Kaizen, or Kaizen Technologies, is a Microsoft National Solutions Partner, and we have gold and silver certifications to stay current with ever-changing technologies. Kaizen offers a variety of solutions that are custom fit to meet any need. I am on the data platform and analytics team, but Kaizen also offers custom app development, managed support, cloud and on-premise solutions. We have physical offices in Louisville, Kentucky and Cincinnati, Ohio, and we work remote or on-site with customers around the globe. A little bit about me. My name is Lucas Fyoke, and I've been with Kaizen Technologies for a little over 5 years. My main skill set is in data warehousing, including the full business intelligence stack. This includes SQL Server, reporting services, integration services, and analysis services, both cube and tabular. I have worked with many different data sets, and a few are listed here. I really enjoy learning and attending events such as SQL Saturday and Past Summit. In addition to that learning, I also enjoy taking exams. My most recent include the Azure AI Engineer, Azure Data Scientist, and Azure Developer. The links below will send you to my Acclaim badges and also links to the really nice professional program that is now Microsoft Learn. You can also connect with me on the links in the left-hand corner. This session's agenda, we will cover the following. What is machine learning? Azure Machine Learning Managed Service, Machine Learning Development Lifecycle, tools that can be used with Azure Machine Learning, integration with other services, machine learning operations or MLOps, and finally a demo of an end-to-end solution using Azure Machine Learning. And so, what is machine learning? To put it simply, it's the ability to train a computer to recognize patterns within a data set. In a more traditional sense, statistics, which we will not cover in this session, is to collect data samples, analyze that data, and find knowledge within it. A classic machine learning introductory example is the Ronald Fisher iris flower dataset. This dataset contains 50 samples from 3 different species of iris flowers: Iris setosa, Iris virginica, and Iris versicolor. Each sample contains measurements of the sepals and petals in centimeters. This data set was collected and handwritten, and then using the linear discriminant analysis manually calculated the function that's used for predicting a species. To get into a more general explanation of machine learning, it has a 2-process, one for training and one for predicting. To start off, in the training process, raw data is collected, cleaned, and a new data set may be added to enhance predictions. This scrubbed up data set is then split into training and testing, usually 70-30, but it can depend upon your data set and what you're working with. The training set is split as well into a train and validate set in order to train your model. Once trained, it is evaluated for accuracy, and either the process restarts or another part is restarted. It's a highly iterative process and often requires multiple attempts to obtain a good model. Like most things related to data and data warehousing, garbage in equals garbage out. But once we have a good model, it can be saved and used for the second process, which is predicting. This starts by collecting a new sample of data, one or more, and applying the required feature engineering to have that data set match what's expected in the model. It is then calculated, and the result is a prediction that can be used to make further business decisions. Azure Machine Learning is a managed service and can be thought of as a PaaS offering or platform as a service. At a high level, Azure Machine Learning allows for preparing data from multiple sources. There are many methods and tools available to clean up data. Training of a model can be done from a versioned data set. This can be done locally or remotely in Azure depending on the size of your data set. Once trained and producing an acceptable accuracy, the model can be packaged up in, say, a Docker image. This model can be managed and versioned as new iterations take place. Once deployed, the model performance can be monitored for data drift. As new data is collected, tasks can automatically kick off actions to retrain the model and deploy a new version. This allows for a full end-to-end lifecycle support for machine learning projects. The machine learning development lifecycle has often been a manual one. Typically, I will have a data set and write a handful of scripts to explore that data. Then create another handful of scripts to massage the data and add new features. That will output a clean data set. that I then copy to a different folder for training a model. That training often produces even more scripts because I'm testing different models and trying different methods. Once something sticks and the accuracy is acceptable, I'll export that model and hand it off to the production team for consumption, or in some cases deploy it myself. Then, months down the road, I'll get a message that the model is not performing well and needs attention. Now I have to go back through all the notes, the scripts, the files, reviewing create times, modified times, and which data file really needs to be updated. It can be a nightmare going back through these things. But with Azure Machine Learning, there is a process that can be followed. And once it is put in place, the task of going back to collect and update scripts can be automated away. And what is shown here are the key steps to wrangling that process. Tools that can be used with Azure Machine Learning include the ML Designer. This is similar to the Azure Machine Learning Studio Classic that allows for drag and drop and lets you create models without a single line of code, or in some cases, a low amount of code if required. Another tool are ML pipelines, which help build and optimize workflows. Once exploration and cleanup is done, and you begin to move into the iteration, a pipeline can be created. Even if it's something as simple as reading a CSV file, it can be part of a pipeline. The benefits of pipelines include simplicity, speed, repeatability, flexibility, versioning and tracking, modularity, quality assurance, and cost control. Automated machine learning, or AutoML, helps remove the time-consuming iterative tasks of model deployment. We will see an example of this later in the demos. You specify the type of learning and a metric, and then Azure AutoML does the training, tuning, model selection, and efficiently uses time and resources. Within Azure Machine Learning, there are notebooks that are available in either Python or R. These notebooks can run on compute instances, which are VMs behind the scenes. They can be accessed by SSH, Jupyter Lab, Jupyter, or RStudio. IDEs and editors can also be used locally for code development and pushed to Azure for training. These include, but are not limited to, PyCharm, VS Code, and Jupyter Notebooks. Another two important features of Azure Machine Learning that utilize reproducible ML pipelines is MLOps, which allows for model management, deployment, and monitoring. Also, integrated CI/CD pipelines, which can be implemented with Azure Repos, Bitbucket, GitHub, or GitHub Enterprise. Azure ML can be integrated with other services, including the following: Azure Active Directory for security, Azure Data Factory, Azure Databricks for ETL. Also, there are multiple data stores that can be accessed, such as Azure SQL DB, Postgres, MySQL, blob and file storage, as well as data lake. For visualization, Power BI and Excel can be utilized. Once a model is deployed, a REST endpoint becomes available that can be consumed by multiple websites. Container services like Docker, Azure CI, and AKS are also available. Azure Open Datasets include publicly available data that has been curated from multiple sources and contributors. These include weather data, satellite imagery, city safety data, public holidays, as well as machine learning samples. MLOps leverages the similar characteristics of DevOps. The goal is to bring together people, process, and technology to continually provide value. With MLOps, we want to achieve the following: creating reproducible pipelines allows you to automate your data preparation, training, and scoring processes. Making pipelines reproducible removes the "well, it worked on my machine" problem. Creating reusable software environments for training and deploying models. Keeping all packages up to date on the same version can be a challenge. Making the environments the same using YAML files enables version requirements to be met. Register, package, and deploy models from anywhere. You can also track associated metadata required to use the model. You can also register models trained outside of Azure Machine Learning. For governance, the logged information can include who published the model, why changes were made, and when models were deployed, and if it's in production. Integration with Git allows us to track the repo, branch, and commit. ML datasets, we can track, profile, and version datasets. The model registry captures metadata about the model and which experiment trained it, where it is deployed, and if it's healthy. We can set up alerts for experiment completions, model registration, model deployment, and data drift detection. Monitoring ML applications allows us to compare model inputs between training and inference, explore model-specific metrics, and provide monitoring and alerts on your ML infrastructure. For example, retraining a model would include the following pipeline: pre-processing your data using a repeatable automated process, training your new model, comparing the outputs of your new model with those of the old, and then using predefined criteria to choose whether or not to replace your old model. Finally, automating the end-to-end lifecycle using pipelines allows us to frequently update models, test new models, and continuously roll out new models alongside your other applications and services. This can be seen similar to DevOps, where a web developer commits a change. In our case, a data scientist commits a change to a Git repo, and that starts training a new model using Azure Pipeline. Then the results can be inspected, and if the performance is above an acceptable limit, can be deployed as a web service. Now, to get into our demos, we'll first look at training a model locally. To get an understanding of a machine learning, then we'll look at creating an Azure Machine Learning workspace. Connect to a data store and create a data set. Train and register a model using Azure ML notebooks. Build a ML pipeline using the designer. Finally, we'll take a look at automated machine learning. Here I have Visual Studio Code and a Python file named train. We will use the iris dataset mentioned earlier, and it looks like this. I will copy and paste code and explain as we walk through it. First, we want to bring in pandas and NumPy, which are typically used for data science. These are libraries that are pre-built and have multiple functions available to us. Next, we want to read in our CSV file of the iris data. Now we want to extract the prediction column from the data set. We create X to hold our features that will be used to make the prediction. Y is the actual values assigned to the data set. For example, Y will be class and X will contain the length and width of sepal and petals. Now, remember back to our machine learning slide where we need to split the data set into training, validation, and test. This next step is where that will take place. We import the library train test split from our sklearn model selection. sklearn is scikit-learn and is another library that's used for data science. Next we have logistic regression. This is where we actually build the model to predict the class of iris. Then we fit the model to the data set that was split. Finally, we run the predictions through to validate the model. In order to determine the accuracy, we need to calculate that based on our actual values and the predicted values, and then print those results to the screen. Here we see the accuracy is 92.1%. Now that we have an acceptable model, we can save it for later predictions. The way to do this is to pickle the model and dump the binary to disk. And now we see that PKL file is available for us. Now let's say we have a new record that we want to predict. This new data file will load the pickle file and take the input values and then predict the class and write it to the console. Here we have the length and width of sepal and petals added to a NumPy array that is then passed into our model to predict. Will return back our class predict, and then that's printed out to the console. And as we see, it predicted it being Iris setosa. And that is a full ML pipeline using a clean data set. In the real world, this process is much more involved, but this shows the general overview of how a machine learning project would take place. we will log in to the Azure portal and we'll create a new resource. You can select AI and machine learning or search for machine learning. Within the Create pane, we will add a name, subscription, resource group, location, and the additions we have our basic or enterprise. For testing purposes, basic allows working with code first. However, enterprise extends the basic workspace and adds user interface, security, and management. So here we have a new workspace filled out with a resource group and the enterprise edition. Next, we can click on Review and Create, and then it will take a few minutes to create the workspace. Now that deployment is completed, we can go to that resource and we can access the workspace. Under Assets, we can view our experiments, pipelines, compute, models, images, deployments, and activities. Later in the demo, we'll review each of these. Since we have Enterprise Edition, we can open up and access the immersive experience that's currently in preview. Here we see similar assets and some additional ones. Under Author, we have notebooks, automated ML, and Designer. Under Assets, we have datasets, experiments, pipelines, models, and endpoints. Under Manage, we have compute, data stores, and data labeling. Before we can get started with this environment, we need somewhere to work. This can be local in an Azure VM or a data science VM. Compute instance is what we will use for this demo. For clusters, inference clusters, and attached compute, there will be links to the documentation in the slides. When setting up a compute instance, we need to give it a name, a VM type, and size. Notice that many VM sizes are available to us. For this example, we'll stick with the default. Once our compute is up and running, we can access notebooks by using either Jupyter Lab, Jupyter, or RStudio. When working with data in Azure ML, we should utilize the data stores and data sets. This allows for versioning of data sets and linking them to specific models. To get started, we click on Data Stores and then New Data Store. We'll give it a name of SQLDB, and under Data Store Type, we have Blob, File, Data Lake, SQL Database, Postgres, and MySQL. We will use Azure SQL Database for this demo. We'll enter our credentials and hit Create. Now that our SQLDB data store is available, we can create data sets from it. We click on Data Sets and Create Data Set from Data Store. We give it a name and leave the dataset type as tabular and click Next. We tell it we want to use the previous data store, and we can pass it a SQL query. It will give us a preview of our query. We can exclude columns if necessary, as well as change the data type. Once everything is acceptable, we'll hit Create. Now we have a data set that we can consume in our notebooks. To do so, we can copy this sample usage to get started. Now we have our Iris data set, our SQL DB data store, and our SQL Saturday compute instance. We can go to Notebooks, we'll go ahead and create a new file. Give it a name of Demo1 and select Python Notebook. Once created, we can click on the Edit button and edit either in Jupyter Lab, Jupyter, or inline. For this case, we will edit in Jupyter. This will open a new tab for us that will automatically sign us in and give us access to a Python 3.6 kernel within a Jupyter instance. If you are unfamiliar with notebooks, this first box is called a cell. It allows for entering text or code. We can insert cells, and each cell can be executed independently from all other cells. The kernel that's running behind the scenes will read the cell contents and either print text or execute code. From our data set, we can copy our sample usage and paste it into our notebook. Similar to our local execution, we'll want to split out the class and the features. Then we'll split the data into test and training. When using Azure ML, we need to create an experiment in order to train our data. Here we'll create a new experiment and pass in the workspace and a name. Next, we want to capture any logs that will take place during this experiment runtime. Here we see the same logistic regression as we had before on our local model building. Here's where we will calculate the accuracy as well as log this to our experiment run. We then save our model to a pickle file and we'll upload that model to our experiment run. Once uploaded, we'll specify the run is now complete. And if necessary, we can view the output of that run. This gives us a link to the details page. Within our experiment, we can see our run number 1 has a metric accuracy of 92.1. The duration took 2 minutes. When we have experiments with multiple runs, we need to determine which one has the best metrics and then use it in order to register it with Azure Machine Learning. We will register our best running model with Azure Machine Learning. Now we can go back to our workspace and view models and see our registered model. That's associated with a specific run ID and a specific experiment. Another tool that we can use is the designer. In here, we can create a new pipeline. First, we need to select our compute target. And then we can add datasets. In our case, we'll bring in the iris dataset. We will want to use a multi-class logistic regression. We'll want to use train a model and we'll want to score and evaluate. We also want to split the data. Here we'll connect our data set to our split, assign our training data to our train model. We'll assign our multi-class logistic regression to our train model. Next, we'll take our testing data, assign it to the scoring model, bring our training model over to score, and finally evaluate the model. We need to enter a label column, which will be our class. And now that we have this set up, we can submit it for a execution run. We can use a existing experiment or we can create a new one. In this case, we can utilize our previous experiment that we used during our notebook training. We can click on View Run Overview and be able to see attributes and other information about our current run. Now that our designer has completed the run, we can either publish this pipeline or create a real-time inference pipeline or a batch inference pipeline. In this case, we will create a new pipeline. We can then click on the name to go to that pipeline. Here we can see detailed information about our endpoint. If we wanted to create an inference pipeline, we would click on real-time or batch. Here we've created a batch inference pipeline that we can then publish. We then have a REST endpoint that we can use to send data and receive an evaluated prediction. One really nice feature of Azure Machine Learning is automated ML. In here, we'll create a new automated ML run. We'll select our data set. We'll configure the run by using a previous experiment. We'll set the target column as our class and select our training cluster as our CPU cluster. It will automatically detect the type of task that we're trying to experiment. In this case, it selected classification. Other cases include regression and time series. To get started, we click Finish. Looking at the details of our voting ensemble best model, we can go into our outputs and see that it generated a YAML file, dependencies, the pickle model, as well as a scoring file. What we can do now is click on Deploy, give it a name for the deployment and where we're going to have our compute, and hit Deploy. Now that the deployment is up and running, we can click on the name for more detail. After a few minutes, our automated ML best model has been deployed. We can click on Dev in order to see details about the endpoint. Here we have our REST endpoint in order to score new data, as well as a Swagger URI in order that tells us the definition of our REST endpoint. And this concludes our presentation. I want to thank you all for attending and watching this video. Please see the links here listed on the screen. If you have any questions, please feel free to reach out to me. Also, this video and slides will be available within the following days. Thank you very much.